All right, so hopefully by now you have tried out the simulation and recognized some of the relationships between the settings that we can change on the simulation and the gravity force and the velocity. So in this video, we're going to be coming up with the equations for gravity and velocity of a planet orbiting a star, or actually any two objects in space for that matter, any two massive objects. So let's start with gravity. So I hope you noticed that there are three variables that affect that strength of that gravity force. So as I change the star's mass, the arrows of gravity force change. As I change the planet's mass, that gravity force changes. And as I change the distance between the sun and the planet, that gravity force also changes. So coming over to my whiteboard, oops. I'm going to write these down. So the mass of the sun, the mass of the planet, and the distance, which I'm going to call r. This is the distance from the center of the sun to the center of the planet. These all affect our force of gravity. It turns out the equation looks like this. Mass of the sun times the mass of the planet over that r value, that distance value, squared, times a constant called g, which is the gravitational constant. This is equal to 6.67 times 10 to the negative 11th. Okay, and hopefully this equation kind of makes sense looking at it, because we know that when we have a fraction, if we make the top of the fraction bigger, the entire value will get bigger. So if I make my mass of my star bigger, my force of gravity should get bigger, and we see that happening over here. Same thing, if I make my mass of my planet bigger, force of gravity also gets bigger, and when I make it smaller, that force of gravity gets smaller. And when I make my r value bigger, when I move these farther apart, that force of gravity gets smaller. So that makes sense because our r is on the bottom of our fraction. Okay, so this equation is known as the law of universal gravitation, because it works for all big objects in space. So any two objects. Doesn't have to just be a sun and a planet. It could be a planet and a moon orbiting it. And we can actually generalize this equation. So sometimes you'll see it written as m2 m1 over r squared times g. m2 is always the bigger mass, the mass in the middle. m1 just represents whatever the smaller object is that's orbiting around. Right. Okay, so next up we're going to look at the velocity of the planet. And I hope you got to recognize that increasing the mass of the star is going to, if you watch this red arrow, very much change the velocity of our object. If I reset this and change the distance that my planet is from the sun, so that r value distance, and I turn on velocity, we're also going to notice that arrow getting bigger, 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 so the velocity is changing. If I change my planet's mass and I start the simulation, you'll notice that my velocity actually isn't changing. Okay, so we're going to do the same thing. We're going to come back over here to our whiteboard, and we're going to write down the variables that did affect our velocity was the mass of the sun and that distance r. This all affects the velocity. And it turns out the equation for velocity is that big G that we talked about earlier times the mass of our sun divided by that distance r. Okay, and again, sometimes you'll see ms equal to m2. Remember, m2 is just the object in the middle, and m1 is rotating around the outside. You'll notice that m1, the planet's mass, is not included in this equation, and in the next video we will talk about why. But for now, this is what you need, the velocity of an orbiting object in space.